So when he switch on and switch off, what is the reference, or why we are saying that when he switch on and switch off? Because when we switch on and switch off the circuit, okay, then the change in the electric current take place, okay, and due to change in electric current, the magnetic field also change. So when he was doing this experiment, okay, he find that when he switched on or switched off, okay, when he switched on or switched off the circuit, he find that there is a deflection in the needle, which is a magnetic needle, okay, placed there. Okay, got it? Are you getting this? Okay, so Hans Oersted, one of the leading scientists in 19th century, plays a crucial role in understanding the magnetism. In 1820, he accidentally discovered that a compass needle got deflected when electric current passed through the metallic wire nearby. Okay, though his observation Oersted show that electricity and magnetism are related, means they are just showing the phenomena. His research later created the technologies like radio, televisions, fiber optics. Okay, this unit of magnetic field strength is named as Oersted in his honor. So the magnetic field, that how a magnetic field his strength is, okay, it is named in his honor, named as Oersted. Okay, so now what we are saying here, that how he noticed that the moving current produce electric magnetic field. How he noticed this one? As we know that if there is a charge particle, this is a q charge particle, and when we bring another charge particle to it, okay, so it will experience a repulsion force here. And when we have a positively charged particle and we bring a negatively charged particle towards it, it will be attracted. So we know that a charged particle exert a force on another charged particle. Okay, got it? Got it?
Yes.
Similarly, when we have a magnet, and magnet was discovered earlier. So when we have a magnet having the north and south pole, and when we bring the north pole and south pole, uh, south and south pole togetherly, they will repel each other. Okay, and when we bring north pole and south pole, and when, okay, opposite poles to each other, they will attract each other. So a magnet exert a force on another magnet. A magnet exert a force on another magnet. Okay, got it? How he noticed that the current carrying conductor produce a current carrying conductor produce magnetic field. How he noticed this one? Actually, when we have a magnet and magnet is being deflected, so magnet can only be deflected by another magnetic force, because a magnetic force exert a force on another magnet. Okay, a magnet, if this needle is being deflected, it means that there are some magnetic field around around this compass needle, which is deflecting it, which is exerting a force on it. Okay, if it is not a magnetic field, suppose if it is not a magnetic field, it is some other field, then it will experience a force. Or if you place a needle which is made up of wood, let wood, the wood needle is not deflected. The wood needle is not deflected. The wooden needle is not, because wood is not a magnet. So if we place a magnetic needle and we change the current in the current carrying conductor, okay, then what is going to happen is that only a magnetic needle is being deflected when a current carrying conductor is bring nearer to it, and when we change the current to it, okay, then it is being deflected. It means that it is the only magnetic field that a current carrying conductor is producing. Understood? Otherwise, if it is not the magnetic force, if it is some other force, then it should experience, means if we put a wooden needle, then a wooden needle should also deflect it. This is a wooden needle, okay, wooden needle, and this is a magnetic needle. Okay, so if I'm talking about that, only the magnetic needle is deflected, the wooden needle is not deflected, it means that there is a magnetic force which is experiencing, or which is exerted by this one. Okay, like for example, if we bring here, and this is the north pole, this is the south pole, if we bring a wooden piece, this is a wooden piece, wooden piece, okay, wooden piece, so it will not exert any force on this one. Okay, but if we bring a magnet nearer to it, it will either repel it or attract it. Got it? You understood?
Yes, sir.
So this is how Oersted knows that this is the only magnetic field that a current carrying conductor produces, because a magnet can exert a force on another magnet. Okay, if the needle is being deflected, it means there is a magnetic force. Got it? Now, after the discovery of this one, that a current carrying conductor produces a magnetic field, so okay, so there is a race that how the scientists start in the means they start researching that how these magnetic field looks like. Okay, how they appears. Okay, so let study this one. Okay, there is an Oersted experiment. Let's study this one first of all. Let's study this one. This is the Oersted experiment. Is the voice is coming to you?
No, sir.
No voice is coming. Okay, just a minute. Is it okay? Just a minute.
Oersted's experiment.
Is it coming to you now?
In
Yes,
1820, Hans Christian
Yes, sir.
Oersted
It's coming.
performed a simple experiment and discovered the magnetic effect of electric current. The experimental setup, similar to the Oersted's experiment, which led to the discovery of magnetic effect of electric current, is shown in the animation. A conductor or conducting wire AB lying in north-south direction is connected to a battery V through a commutator or tapping key K and rheostat RH. A magnetic compass needle NS is placed just below the conductor AB. Initially, when no current passes through the wire AB, the magnetic compass needle shows no deflection. When an electric current passes through the wire placed above the compass needle, the magnetic compass needle got deflected from its normal position, which is along north-south direction. On reversing the direction of electric current through the wire, he observed that the magnetic compass needle got deflected in the opposite direction. Also, the deflection of the compass needle increased when the magnitude of electric current through the wire was increased or when the compass needle was brought closer to the wire.
Understood? Or should I
yes,
repeat it? Understood? Means
सर आवाज ही नहीं आई
सर ऑडिबल ही नहीं था.
okay. 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 Got it? Got it? Saima, you understood? Now, what actually, if I talk about that, the scientists start in search that how
Yes, sir.
how actually how actually these magnetic field lines look. Okay, so they start searching, means that how actually the magnetic field lines looks to each other. So actually there was a bar magnet was taken on a paper. Okay, and when we took the bar magnet, okay, we took a bar magnet, okay, and there is a scientist start searching that how this magnetic field lines actually, what is magnetic field, what is magnetic field. Magnetic field is a field or an area around the magnet up to where its force can be exerted, or the force of magnet can be experienced. So what is magnetic field? It is an area around the magnet, around the magnet up to where its force can be its force can be experienced. Okay, got it. So now how does magnetic field lines look actually? So we did our experiment, and how we did the experiment actually, first of all, let me tell you that how we got the north pole and south pole. Okay, so we know that earth is going to have this is the earth. Okay, and it is going to have its own magnetic field, so if it is, this is earth. Okay, so earth has its own magnetic field. We imagine that there is an imaginary bar magnet present inside the earth, which is one-fifth of the diameter of the one-fifth of the diameter of the earth. Okay, so it is one-fifth of the diameter of the earth. Okay, so what we actually here we imagine here is that if this is the actual north pole and this is the south pole. Okay, how does we know that this is the north pole and this is the south pole? When we place a bar magnet, okay, over a surface of the earth, okay, over the surface of the earth, we find that a needle compass with an arrow. Okay, we arbitrarily choose that the arrow represent the north, and this opposite, this we can say that tail represent the south. Okay, so when we placed it on the on the surface of the earth, so this magnetic needle always point towards a direction. When we kept it, if I kept it here, okay, so it will point like this. If I point it like here, it will point like this. Okay, if I point it here, it will point like this. So it always point towards north and south. It always point towards a particular direction, north and south. Okay, so we just put it at the north and the south, but actually the magnet that is present inside the earth, it is going to have south pole here, and this is the north pole. So actual geographical north and the magnetic north and magnetic south lies in the same direction. Okay, and geographical south pole and the north pole of the bar magnet or the imaginary bar magnet that is present inside the earth or earth magnetic field is, okay, this is actually, it is actually the opposite here. Okay, it is actually the opposite here. So here we can say that the north pole and the south pole, okay, the north pole and the south pole lies together in the same direction. Okay, they lies in the same direction, but they are opposite. You can consider that the south pole of the magnet and the north pole of the geographical north lies in the same direction. Why? Because we know that like poles repel each other. Like poles repel each other. This is south, this is north. Okay, and if it is south, it is north. So they will repel each other. Okay, so when we bring a compass needle over the on the surface of the earth, then it always point. If it is south pole, then here the north pole will comes or point towards it. Okay, so they repel each other. So let you see this video, and this video will going to help you. Okay, let you see this one. Just a minute.
Direction in which a magnet points changes from place to place on Earth.
Is I'm audible to you, Sama?
Yes, sir.
Okay. So you can just a minute. Just a minute, coming back.
Up to 528,000.
Just listen to this one. That in this one, this video is showing
Terrestrial magnetism. A freely suspended bar magnet approximately points towards the geographical north.
so you need to understood here that that when we are just going to have always you need to keep in mind that the geographical north and there is a south pole, but actually the bar magnet that is of earth bar magnet, okay, that is earth bar magnet that always lies in opposite directions, that always lies in opposite direction. Okay, just let me explain you here.
Terrestrial magnetism. A freely suspended bar magnet approximately points towards the geographical north with its north pole and the geographical south with
Just a minute.
its south pole as it comes to rest. This is also known as the directive property of a magnet. The direction in which a magnet points changes from place to Earth. Similarly, when a magnetic needle is pivoted at its center and allowed to a vertical plane along its north and south, it does not remain vertical but remains inclined to it. This inclination also changes from place to place on Earth.
So you can understood here that when we are just going to have
May be imagined as a giant bar.
there is a giant bar magnet that is present inside the earth. Okay, and they are just imaginary, that is an imaginary giant bar magnet that is present inside the earth, and that magnet actually has opposite poles. Okay, okay, on the geographical north and south, and these are the magnetic poles of the south and north here. So this is the imaginary bar magnet. Okay, and why the earth is going to have the bar magnet and why it is going to have magnetic field, that is the case of higher, means you need to study this one in the high classes, so no need to worry about it. So how actually the magnetic field lines we have. Okay, so just imagine this is a bar magnet, imagine this is a bar magnet, or this is north pole and this is the south pole. So we if we keep a compass needle here, we will find that this will deflect here like this way. When we keep a magnetic needle here, this will deflect like this way. When we keep a magnetic needle here, it will deflect like this way. This keeping on this one, okay? When we keep on putting the bar needle magnet, okay? We find, we find that these magnetic needles point like this. They start pointing like this. So we according to the arbitrary chosen the direction that this arrow represent the north pole and this arrow represent the south. So we just understood that the magnetic field lines move from north to south outside the bar magnet. Okay, so we just consider this one, that the magnetic field lines move outside the bar magnet. They move from north to south. Here it is, north pole is written here, but in I have made it like this way. So north pole here. So according to my diagram, if north pole is this one, if this is north pole, this is south pole, the magnetic field lines move outside the magnet like this. They move like this. Okay, they move like this. Got it? From north to south. From north to south, they move like this. And the very importantly thing is that since the magnetic field lines that are coming from the north pole, okay, and here they are distributed into two halves. So half is going to this way, half is going to this way. So at the middle of this one, okay, we are not going to have the strong magnetic field or magnetic field lines, but here at the poles the magnetic field is very strong, because half of the magnetic field lines that are coming, they are also going to converge here, and half of the magnetic field lines that is coming from here, they are going to merge here. So all the magnetic field lines which is above the half or below the, we can say that, which is above this one or below this one, they are going to merge at the poles. So the magnetic field strength is higher at the poles. Got it? And moreover, magnetic field lines never intersect each other. The property of magnetic field lines is that they outside the magnet, they move from north to south, north to south. Okay, like this. Outside the magnet, they move from north to south. And inside the magnet, they move from south to north in a straight line. In a straight line. This is very important, that you need to keep in mind, that outside the magnet, they move from north to south, and inside the magnet, they move from south to north. Okay, and they never intersect each other. Why they don't never intersect each other? Because if they intersect, then at the point of intersection, okay, if they intersect, then at the point of intersection, there must be 2 points. The magnetic needle should deflect in 2 directions. Let me explain you one more time. That imagine that this is the north and south pole, and if these magnetic field lines are going to intersect, let's suppose they intersect here at this point. Okay, so when you put the compass needle here, it should deflect in this direction also and in this direction also. But it is not practically possible that a needle is going to deflect in 2 directions. So we just say that the magnetic field lines never intersect each other. So why do magnetic field lines never intersect each other? Tell me, Taima. Why do magnetic field lines never intersect each other? Tell
Because
me.
if it affects, then
Because,
the magnetic needle will have to affect in
सर
two
अगर वो
directions.
इंटरसेक्ट करेंगे
yeah.
तो सर वो मैग्नेटिक कंपास 2 डायरेक्शन शो करेगा सर जो पॉसिबल नहीं है.
So yeah, okay, it is correct that if they intersect, then at the point of intersection, okay, we can simply say that the magnetic needle must show the 2 directions, and which is not practically possible. So if the question comes in examination that why do magnetic field lines never intersect each other, so the only reason for this one is that if they intersect, then at the point of intersection, the magnetic needle line will point towards 2 direction, which is not practically possible. Got it? Got it? So should I write this answer, or will you able to wrote it by your own? Tell me, Simon.
Sir, I can write it on my own.
Okay. Now here we just going to have some picture. Let me show you.
Ørsted's experiment.
Here we have an experiment here to show that.
Ørsted's experiment.
We know that a current carrying conductor
Now we need to understood here that we know that a current carrying conductor behave as a means it behave as a magnetic magnetic field is shown by a current carrying conductor. Okay, now the property that how the magnetic field lines look like. Okay, so there are so many assumptions that a current carrying conductor can have a current carrying conductor can have a spiral magnetic field lines. It can have a magnetic field lines like this. Okay, like this it can have. Okay, in the outward direction. Some says that they are going to have magnetic field lines in the square shape. So there are so many assumptions that a magnetic field lines, a current carrying conductor is going to have a magnetic field lines. But actually, when we did the experiment, we find that the magnetic field lines shown by a current carrying conductor is in the form of concentric circles. So if this is a current carrying conductor, okay, so we can say here that if this is a current carrying conductor, so the magnetic field lines will be in the form of concentric circles. Okay, which is what are concentric circles? Concentric circles are the circles which we can simply say that which is going to have the same centers. Okay, got it? So here this experiment is going to show you that how we know that the magnetic field lines of a current carrying conductor is in the form of concentric circles.
We know that a current carrying conductor behaves like a magnet. So, what is the pattern of this magnetic field? Let us do an activity to find out the pattern around it. We know that a current carrying conductor behaves like a magnet. So, what is the pattern of this magnetic field? Let us do an activity to find out the pattern around it. We have taken a straight, thick copper wire connected to an electric circuit to pass current through it. And iron filings in a sprinkler.
This is we are going to have an iron filling in this one. Okay, and we are just having a
Sprinkle
current
iron filings around the conductor.
This is the current carrying conductor, and when we sprinkle the iron fillings over it, then we will find that there are some patterns that are formed here. Okay, so this is not going to have the
Insert the plug key and observe. We can observe that the iron filings are aligning in a pattern of concentric circles. These represent magnetic field lines. Let's place the compass over these lines. The direction of the north pole of the compass represents the direction of these magnetic field lines. By moving the compass over the lines, we can see the direction at each point. By moving the compass away from the conductor, we can see that the deflection of the needle decreases. It indicates that the magnetic field decreases as the distance from it increases. It can be noticed by the larger circles formed away from the conductor. So, we found that a straight conductor carrying current produces concentric magnetic field lines around it.
Download.
Now you understood? Now you understood that how the magnetic field lines around a current carrying conductor is. Now you can see here that a current carrying conductor is going to have the concentric circles lines. Okay, and if these lines have a particular directions, and what is the direction of this one is this can be obtained by this can be obtained by right hand thumb rule. So what does the right hand thumb rule states? Right hand thumb rule. So what does the right hand thumb rule is going to say? That if the current, imagine that you are holding a current carrying conductor in your right hand. Okay, Imagine that you are holding a current carrying conductor in your right hand such that the thumb point the direction of current. Then your curl finger will point the direction of magnetic field lines. Okay, got it? The curl finger will point the direction of magnetic field lines. So let me explain you in more detail that how can you imagine this one. Just imagine that this is a 3D box I'm just making here to explain you more betterly, and this will help you to understood in a better manner that how can you predict whether it is clockwise or anti-clockwise. Okay, whether current is clockwise or anti-clockwise. Okay, and the magnetic field lines. Okay, here just imagine that a current that your eye is here. Okay, and you are looking it downward. Okay, and the current is coming towards you. If the current is coming towards you, just imagine that if the current is coming towards you, so it means the current, you just imagine yourself, for an human beings, a current is considered to be as anti, means human beings are anti. Are you getting my point? Human beings are anti current. We can say that we don't like current. If someone is bringing the wire towards you, then you will move away from it. Okay, so just imagine that if this current is coming towards you, if you're watching this one and the current direction will be towards you, then the magnetic field lines will be anti-clockwise. Magnetic field line will be anti-clockwise. Are you getting my point? Anti-clockwise. Okay, and if it is going away from you, then it will be, if for example, if your eye is here and you are watching it from here, and the current is going like this, the current is going in the wire like this, so here the direction of the magnetic field lines will be clockwise. If the current is going away from you, then it will be clockwise, and if the current is coming towards you, then it will be anti-clockwise. So the current is coming towards you. If you are observing from here, then from here, if you observe it from the top, then it will be anti-clockwise. Anti-clockwise means like this. Okay, like this, anti-clockwise. And if the current is going away from you and you are watching from here, then it will be clockwise, like this. Got it? Clockwise. So here, if you are watching it from the top, okay, if you are observing from this top, so here the direction of current will be it coming towards you, and for towards you it will be anti-clockwise. Got it? Understood? It will be anti-clockwise. So this is also given by right hand thumb rule. How right hand thumb rule state that if you are having your thumb like this, it is pointing towards the direction of, okay, like this, and you are holding a current carrying conductor in your right hand. Just imagine that you are holding a current carrying conductor in your right hand, and the current is moving towards your right hand. Then your curl finger will point the direction of magnetic field line. So here, if you curl it, okay, here if you curl it, then the magnetic field lines will be how it is showing. You will feel that this will be coming like this. So this will be coming like this. This is your thumb, then your fingers, then it is. So it will be like this. Okay. So this is anti-clockwise direction. So this is a simple thing that if the current is going away from you, then it is clockwise. If the current is coming towards you, then it is anti-clockwise. Are you getting my point? You understood, Simon?
Yes, sir.
Understood. So what does right hand thumb rule states? Right hand thumb rule state that imagine that you are holding a current carrying conductor, in your right hand, okay. Imagine that you are holding a current carrying conductor in your right hand such that the thumb point the direction of point the direction of current, then your curl fingers will point the direction of we'll point the direction of magnetic field lines. Okay, magnetic field lines. Note it down, please. This is the right hand thumb rule. Note it down fast. Noted? Tell me fast.
Answer.
Now, what type of numerical problem is being asked on this topic? Actually, first of all, the direction of current. Let me explain you what is the direction of current should be taken and when it is taken. Okay, direction of current. Actually, the direction of current is direction of current. So if I talk about what is the direction of current, the direction of current is arbitrarily chosen from positive terminal to negative terminal. Direction of current is arbitrary chosen, means it is chosen by our will. Okay, chosen from positive terminal to negative terminal. Okay, and we can say that it is same as the direction of flow of positively charged particle such as proton, comma, alpha particle, etc. And it is opposite, and it is opposite to the direction of flow of electron. It is opposite to the direction of flow of electron. Note it down fast. Noted? Tell me. Noted this one?
Noted.
Okay.
Yes, sir.
Now moving to the next part here is that the questions comes in examination that how, for example, if let's suppose this the direction of this one, let's have the direction. Let's make this box again, and how the questions usually comes in the examination. So tell me, inside the magnet, the magnetic fields are uniform, okay? And it is from south to north. And outside the magnet, it is non-uniform. And it is from north to south. Will you keep in mind? Will you remember this one about the magnetic field lines? So most important question that is being asked in the examination is, why do magnetic field lines never intersect each other? Okay. So let we are having this one as, this one is west, this one is east, and this one is north here, and this one is south. Okay. If the question comes in examination that you are observing an electron is projected, from east to west. Question comes, an electron is projected from east to west. What will be the direction of, the direction of magnetic field lines just above the wire when observed just above the wire. Tell me, will it be from north to south? First option is from north to south. The second option is from south to north. The third option is from west to east. And fifth option is from east to west. Tell me, which is the correct option?
North to south.
Okay. So tell me, Saima, how will you observe? And how will you predict this one? What is saying that this is the north-south, electron is projected, and you are watching electron, you have to tell the position here, just above the wire, that will it be north to south, south to north, east to west, like this? Like it is north to south like this, it is south to north like this. Tell me, what should be the direction?
North to south.
North to south. So you see that if the electron is projected from west to east, east to west. If the electron is projected from east to west, then the direction of current will be east to west to east. This is the direction of current. Got it? Got it?
Yes, sir.
Now, if this is the direction of current, I is the direction of current, okay, and you are observing, it is given that when it is observed just above the wire, you need to tell us. So if you are just observing from here, just imagine that you are observing from here. So if the current is coming towards you, okay, then it will be anti-clockwise.
Sir, it's east to west, right?
No. Here an electron is projected from east to west. So if the electron is moving from east to west, then the direction of current will be west to east. It is opposite. You need to keep in mind. You need to do it by using right hand thumb rule, but the direction of the current should be taken properly. If the electron is moving from bottom to up, then the direction of the current will be opposite to this one. If the electron is moving to this direction, then the direction of current will be opposite to this one. This is arbitrary chosen. The direction of current is always opposite to the direction of flow of electron. Got it? Got it?
Yes, sir.
So here the question comes that if the electron is moving from east to west, then the direction of current will be from west to east. Now imagine that you are watching it from here, from east. So what you will watch? You will watch here that the current is coming towards you, and when the current is coming towards you, then it is anti-clockwise. Then it is from here, it is anti-clockwise. So here, just make a circle here. Just make a circle here. Okay, and it is anti-clockwise. So it will be from north, okay, to south. North to south. Above the wire, it will be north to south because it will be moving like this. Anti-clockwise direction is like this because clock will move. If it is 12, this is 3, this is 9. So anti-clockwise is like this. Got it? Got it? If a wall, imagine that a wall is placed here, 12, 3, 9. So it will be like this. So anti-clockwise is from north to south. Got it? Got it? So if the current
Yes,
is coming towards you, it is north to south. So just above the wire, it will be from north to south. And if I ask you the same question that just below the wire, so just below the wire, it will be like here, and it will be from south to north because this is anti-clockwise direction. Got it? Got it?
yes.
So here is a question. Let you do this question. Question number 9. What you will answer this question? Question number 9. Tell me, what should be the answer for question number 9? Okay, should I help you?
So is the answer D?
At the point located plane of the paper on the south side of the wire. Let's study this one. Like this is a, again, whenever you are having such type of problem, just make the box first. Just make the box first. Okay. And after making the box, just place north and south like this, so that you will not feel any difficulty. Okay. A constant current can conduct flows wire. A constant current flows in a horizontal wire in the plane of the paper from east to west. So this is west, this is east. Okay, this is north here, and this is south here. Okay. Now from west, as shown in here, from east to west means current is flowing in the plane of the paper from east to west. So it is flowing from east to west. Okay. The direction of magnetic field lines, the from north to south. Now the direction of magnetic field lines. So if you are observing, and from where you are observing this one. Now you see here that just you are observing from here. You can choose any direction. If you choose here from east, that you are observing it from here. Okay. If you are observing from here, then it is going away from you, and away from you it is clockwise. So clockwise will be like this. Clockwise will be direction like this. So above the wire it will be south to north. Okay, and below the wire it will be north to south. So what is it asking? The direction of magnetic field lines at a point from north to south. So north to south will be below the wire. Okay, the B is the correct answer. Below the wire. Just below the wire. And here, what is saying that a point located in the plane of paper? No, it should not be located in the plane of paper. It is just below the paper. Okay, point located on the plane of the paper? No. Okay, plane of the paper should not be there. It is below the paper or above the paper. So above the paper, since we are observing from east, and it is moving like this, so it is moving away from us, from east to west. The current is moving, so it will be anti-clockwise. If it is clockwise, because it is moving away. So if it is clockwise, so above the wire it will be from south to north, and below the wire it will be from north to south. You understood?
Yes.
Understood? So this way you have to practice this one. Got it? Got it?
Yes, sir.
So we'll,
Yes, sir.
we'll send you some question regarding to this one. You have to solve this one. And here, last question, one more last question. Choose the correct statement of the following regarding the magnetic field lines. Which is the correct? A, B, C, D. Which is the correct? Incorrect one.